And now in this lecture we'll find out the area of trapezoid ABCD. In the drawing we have trapezoid ABCD. We know that side AB equals to line segment AP in its length. We also know that line segment PD is equal to side DC in its length. This is line segment BQ that is equal to 4 units in its length. This is line segment QC that is equal to 9 units in its length. Those two angles are right angles. And this is angle PQC that is also a right angle. Again, our mission is to find out the area of this trapezoid ABCD. So, first of all, if we focus on, we know that BC is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the left side of the straight line BC at point Q here, the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line BC at point Q? We have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. It is given us in the question that side AB equals to line segment AP. So if we define the length of side AB as A, then AP must be also equal to A because they are equal to each other. Likewise, it is given us the question that line segment PD is equal to side DC in its length. So if we define the length of side PD as B, then the length of side DC must be also equal to B because they are equal to each other. In the next step, we'll join points B and P together by straight line. And also join points P and C together by straight line. By joining points P and B, we created the right triangle. We created here the right triangle PAB. So we focus on this right triangle PAB. This right triangle PAB, side AP equals to side AB. Therefore, it is a right triangle and it is also an associated triangle simultaneously. And we have the rule that says that in front of equal sides in the triangle there are equal angles. So in front of this side AB is equals to A, we have this angle. And in front of this side AP is equals to A, we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must be equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. Because of the fact that they are located in front of those two equal sides, they must be also equal to each other in their sizes. We know that the sum of the angles in any triangle is equal to 180 degrees. Especially it is true in the right triangle APB. So which angles we have in the right triangle APB? We have, this is a right angle, that is to say it is equal to 90 degrees, plus alpha, that is plus 2 alpha. In total, the sum of those angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So 90 degrees plus 2 alpha must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. So 2 alpha equals to 90 degrees. Here we divide this equation by 2. And we get that alpha equals to 90 degrees over 2, that is 45 degrees. So this is angle alpha, that is equal to 45 degrees in its size. And this is also angle alpha, that is equal to 45 degrees in its size. So in total, we found out that whenever you have a right triangle that is an isosceles triangle, those two angles must be equal to 45 degrees. Actually, in the right triangle PDC, in this right triangle PDC, side PD equals to side DC, and therefore it is a right triangle that is an isosceles triangle. And therefore, those two angles must be equal to 45 degrees each one. You don't have to repeat all the same process. We only found out that whenever we have a right triangle that is also an isosceles triangle, those two angles must be equal to 45 degrees. Therefore, those two angles must be also equal to 45 degrees. In the next step, we'll focus on the left side of the straight line AD at point P. AD is one side of the trapezoid ABCD, therefore it is absolutely straight line. So if we focus on the left side of the straight line AD at point P, the sum of the angles on the left side of the straight line AD at point P must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the left side of the straight line AD at point P? We have 45 degrees plus 45 degrees, that is 90 degrees, plus this missing third angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this third missing angle must be equal to 90 degrees in its size. Why? Because 90 degrees plus 45 degrees plus 45 degrees, in total it is 180 degrees. That is the sum of the angles on the left side of the straight line AD at point P according to rule 3. So the missing third angle must be PQ, BPC must be a right angle. So in the next step we'll focus on the right triangle PQC, on this right triangle PQC. And we define this angle as alpha. So in the right triangle PQC, this angle equals to 90 degrees, this angle equals to alpha, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. The big angle BPC is equal to 90 degrees in size. This is angle alpha, therefore this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. That is exactly the size of the big angle BPC. That is the right angle. Okay, so in the small right triangle BPQ, this angle equals to 90 degrees minus alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in a triangle. In the next step, we'll prove that the small right triangle PBQ is similar to this big right triangle PQC. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles, they are both right angles, and therefore they are equal to each other. So in total, we found out that all the figures of the right small triangle PBQ are correspondingly equal to all the figures of the right big triangle PQC, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We found out that the small right triangle PBQ is similar, this is the sign of similar, to the right big triangle PQC, according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side BQ of this small right triangle BQP over side PC of this big right triangle PCQ actually side BQ of the small right triangle PBQ over side PQ of the big right triangle PQC is equal to side PQ. Actually, PQ is a common side that belongs to both triangles. PQ belongs to the small triangle PQB, and PQ also belongs to the big right triangle PQC. So PQ is a common side that belongs to both triangles. And also side PQ of the small right triangle PQB over side again side BQ of the big right triangle PBQ over side PQ of the small side BQ of the small right triangle of the small right triangle PBQ over side PQ of the big right triangle PQC is equal to side PQ of the small right triangle PQC of the small right triangle PQB over side QC of the big right triangle QCB. Okay, again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side PQ of the small right triangle PBQ over side PQ of the big right triangle PQC is equal to side PQ of the small right triangle PBQ over side QC of the big right triangle PQC. BQ equals to 4 units in itself according to what is given as the question, so the substitute BQ by 4 over PQ. PQ is the missing side, so leave it as it is. We have again PQ, because PQ is a common side that belongs to both triangles, over QC. QC equals to 9 units in itself according to what is given as the question. So in total, we have found out that 4 over PQ equals to PQ over 9. Here we cross multiply this equation, and we get that PQ squared is equal to 4 times 9, that is 36. PQ squared equals to 36. Here we take a root out of this equation and finally we get that PQ equals to the square root of 36, that is 6. So the length of side PQ is equal to 6 units. So write it down. PQ equals to 6 units in its length. In the next step, we'll implement the Pythagoras theorem on this right big triangle PBC. This is the big right triangle PBC. Here by PT is a relation for Pythagoras theorem. Again, we implement the Pythagoras theorem on this big right triangle PBC. According to the Pythagoras theorem, in this big right triangle PBC, actually according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. So BC squared, that is the square of the hypotenuse, is equal to PB squared plus PC squared. It again in the big right triangle PBC, according to the Pythagoras theorem, BC squared, that is the square of the hypotenuse, equals to PB squared plus PC squared. In the right triangle PBC, according to the Pythagoras theorem, BC squared, that is the square of the hypotenuse, equals to PB squared plus PC squared. What is the length of BC? BC in total equals to 4 plus 9, that is 13. BC is 13, therefore BC squared is 13 squared, that is 169, and it is equals to PB squared. PB squared, what is the length of PB squared? PB squared, we have APB is the right angle, and according to the Pythagoras theorem, in this right angle APB, A squared plus A squared equals to PB squared. Again, in this right angle ABP, in this right small triangle ABP, A squared plus A squared equals to PB squared. So PB squared equals to A squared plus A squared, that is 2A squared. We substitute PB squared by 2A squared plus PC squared. PC squared. What is the value of PC squared? Again, we have PD squared, that is the right angle. PDC is the right angle. In the right angle PDC, according to the Pythagoras theorem, PC squared, that is the value that we are looking for, is equal to B squared plus B squared. So in total, PC squared equals to B squared plus B squared is 2B squared. So we substitute PC squared by 2B squared. So in total, we found out that 169 equals to 2A squared plus 2B squared. So 169 equals to, here, take 2 as a common factor out of this, for those two expressions. So inside the brackets, we have A squared plus B squared. So if we found out that 169 equals to 2 times A squared plus B squared. Here we divide this equation by 2, and finally we get that A squared plus B squared equals to 169 over 2. So write it down again. If we found out that A squared plus B squared equals to 169 over 2. And again, if we found out that A squared plus B squared equals to 169 over 2. Our mission is to find out the area of this trapezoid ABCD. So what is the area of trapezoid ABCD? from the drawing it is very easy to see that the area of trapezoid ABCD, actually trapezoid ABCD contains three right triangles. It contains the right triangle ABP, and it also contains the right triangle PDC, and it also contains the big triangle PBC. And therefore, the area of trapezoid ABCD must be equal to the area of the three right triangles that it contains. That is to say, it must be equal to the area of this right small triangle ABP plus the area of the big triangle PBC, the big right triangle PBC. This is the big right triangle PBC. Plus this triangle PDC. So if we found out that the area of trapezoid ABCD must be equal to the area of the three components that it consists of. Trapezoid ABCD consists of the right triangle ABP plus the right triangle PBC plus the right triangle PDC. In total, the sum of the areas of those two three triangles must be equal to the area of trapezoid ABCD. So what is the area of this right triangle ABP? The area of any triangle equals to the base times the height over 2. That is to say, it is AB times AP over 2. AB is A, AP is A, so it is A times A over 2. A times A is A squared over 2. So the area of this triangle ABP is equal to A squared over 2. What is the area of this triangle PBC? The area of triangle PBC equals to the base, that is BC. The base is BC times the height. The height is PQ. Why the height is PQ? Because of the fact that PQ creates 90 degrees with the base BC. So the height is PQ over 2 plus the area of this right triangle PDC. What is the area of the right triangle PDC? It is equals to the base, that is DC, times the height, that is DP, over 2. The base DC is B, the height DP is also B, divided by 2. So it is B times B over 2. That is to say, it is B squared over 2. So in total, if you found out that the area of triangle ABC equals to A squared plus B squared over 2, A squared plus B squared over 2, plus BC in total equals to 4 plus 9, that is 13. Yeah, BC in total equals to 4 plus 9, that is 13. Times PQ, the height PQ is 6, divided by 2. So in total, the area of trapezoid ABCD equals to A squared plus B squared over 2, plus 13 times 6 over 2. But we have already found out that A squared plus B squared is equals to 169 over 2. Therefore, we substitute A squared plus B squared here by 169 over 2. So A squared plus B squared is 169 over 2 divided by 2 plus 13 times 6 over 2 is 6 times 2, that is 3. and 3 times 13 is 39. So in total, the area of trapezoid ABCD equals to 169 over 2 times 2, that is 4, plus 39. So here we multiply 39 by 4 and then we divide it by 4 in order to have a common factor with this number, and we get that 169 over 4, and 39 times 4 is 156. So in total, the area of trapezoid ABCD equals to 169 plus 156 over 4. 169 plus 156 is 325 over 4. 325 over 4 is 81.25 square units. So in total, if you want the area of trapezoid ABCD is equal to either 325 over 4 square units, so in terms of numbers, it is equal to 81.25 square units. And that is the answer to the question. So, in the next step, I'll summarize the lecture. In this lecture, our mission is to find out the area of this trapezoid ABCD. So in the drawing, we have trapezoid ABCD. We know that side AB is equal to line segment AP. We also know that line segment PD equals to line segment DC. We also know that this is line segment BQ, this is equals to 4 units in its length. This is line segment QC, this is equals to 9 units in its length. Those two angles are right angles, and this is angle PQC, that is also right angle. Again, our mission is to find out the area of this trapezoid ABCD. So, first of all, we know that BC is one side of trapezoid ABCD, therefore it is absolutely a straight line. So, if we focus on the left side of the straight line BC at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3, that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line BC at point Q? We have this angle that is 90 degrees according to what is given us the question, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. It is given us the question that AB equals to line segment AP in its length. So if we define the length of AB as A, then the length of line segment AP must be also equal to A, because they are equal to each other in their lengths according to what is given as the question. Likewise, it is given as the question that line segment PD is equal to side BC in its length. So we define the length of line segment PD as B, then the length of side DC must be also equal to B, because they are equal to each other in their lengths according to what is given as the question. In the next step, we focus on this right small triangle ABP. This small right triangle ABP. We know that those two sides are equal to each other, and we have the rule that in front of equal sides in the triangle are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other in their sizes. So if we define the size of this angle as alpha, then this angle must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. So those two angles, they are both equal to alpha. So in the right triangle ABP, the sum of the angles must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right triangle ABP? We have this angle that is a right angle, that is to say 90 degrees, plus alpha plus alpha, that is 2 alpha. Total, they must be equal to 180 degrees according to the rule that I mentioned. So 90 degrees plus 2 alpha equals to 180 degrees. So here we subtract the 90 degrees from this equation, if I found out that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. So here we divided this equation by 2, and finally found out that alpha equals to 90 degrees over 2, that is 45 degrees. So those two angles are both equal to 45 degrees. Okay, so actually I can conclude for me that whenever you have a right triangle that is also an isosceles triangle, then one angle is of course a right angle, and the two other angles they are equal to each other, and the size of each angle is 45 degrees. So here we have also triangle PDC is a right angle that is also an isosceles triangle. What is an isosceles triangle? Because side PD equals to side DC. And therefore, those two angles must be equal to 45 degrees in their sizes. And don't have to repeat on the same process in order to prove that those two angles, each of them is equal to 45 degrees. Okay? So, in the next step, we joined points B and P together by a straight line, and also joined points P and C together by a straight line. Okay, so and actually we already done this step. We have here two right triangles. We focused on the left side, on the right side of the straight line AD at point P. AD is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if you focus on the right side of the straight line AD at point P, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AD at point P? We have this angle that is 45 degrees plus this angle that is 45 degrees. In total they are 90 degrees. So 90 degrees plus this third facing angle, in total they must be equal to 180 degrees according to rule 3. Therefore, this third facing angle must be equal to 90 degrees in size. That is to say, the missing angle BPC is a right angle. Okay, angle BPC is a right angle. In the next step, we focus on the right triangle PQC. The right triangle PQC, we define this angle as alpha. And because of the fact that the big angle PQC is a right angle, that is to say, it is equal to 90 degrees in size, and this angle is alpha, therefore, this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. That is the sum, the size of the big angle BPC. So this missing angle must be equal to 90 degrees minus alpha. So in the right triangle PQC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees. That is the sum of the angles in the triangle. Likewise, in the small right triangle PBQ, this angle equals to 90 degrees minus alpha, this angle equals to 90 degrees, and therefore this third angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees. That is the sum of the angles in the triangle. In the next step, we prove that those two right triangles are similar to each other according to angle similarity rule. So, why the right small triangle PBQ is similar to the right big triangle PQC? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I shall prove that all the figures of the small right triangle PPQ are corresponding equal to all the figures of the big right triangle PQC, therefore those two right triangles are similar to each other according to angle similarity rule. So I repeat again, if you found out that the right small triangle PBQ is similar. This is the sign of similar to the right big triangle PQC according to angle similarity rule. And for the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We derive that side BQ of the small right angle PBQ over side PQ of the big right angle PQC is equal to side PQ of the small right angle PQB over side QC of the big right angle PQC. Side PQ is a common side that belongs to both angles. Side PQ belongs to the small triangle PQB, and side PQ also belongs to the big right angle PQC. Okay, again, for the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. That side BQ of the small right triangle PBQ over side PQ of the big right triangle PQC is equal to side PQ of the small right triangle PQB over side QC of the big right triangle PQC. BQ is 4 according to what is given as the question over PQ. PQ is the missing side, so leave it as it is, and it is equal to PQ. Again, PQ is it is the missing side over QC. QC is 9 according to what is given as the question. So in total, we shall find out that 4 over PQ equals to PQ over 9. Here we cross multiply this equation and finally found out that 4 times 9, that is 36, is equal to PQ square. Again, PQ square equals to 36. We took out of this equation and finally found out that PQ equals to the square root of 36, that is 6. So this is side PQ that equals to 6 units in its length. In the next step, we implemented the Pythagoras theorem on this big right angle PBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the big right triangle PBC. The hypotenuse in this big right triangle PBC is BC. The square of the hypotenuse is BC squared, and it is equal to BP squared plus PC squared. Okay, again, according to the Pythagoras theorem, the big right triangle PBC, BC squared, that is the square of the hypotenuse, equals to PB squared plus PC squared. BC in total equals to 4 plus 9, that is 13. Therefore, BC squared equals to 13 squared, that is 169. BC squared is 169, and this is equals to PB squared. PB is equal to PB squared. PB, what is the value of PB? We'll focus on this small right triangle APB. According to the Pythagoras theorem, in this small right triangle APB, A squared plus A squared equals to PB squared. So PB squared equals to A squared plus A squared, that is 2A squared. Again, PB squared equals to 2A squared. And we have also plus PC squared. What is the value of PC squared? So if you focus on the right triangle PDC, PC squared, that is the square of the hypotenuse, equals to B squared plus B squared. So PC squared equals to 2B squared. PC squared equals to 2B squared. So in total, we found out that 169 equals to 2A squared plus 2B squared. So 169 equals to, here we took 2 as a common factor out of this expression, so inside the brackets we have A squared plus B squared. Here we divided this equation by 2 and finally found out that A squared plus B squared equals to 169 over 2. Okay, again, I should have found out that A squared plus B squared equals to 169 over 2. Our mission is to find out the area of this trapezoid ABCD. This trapezoid ABCD consists of 3 right angles. It consists of this right small triangle APB, and it also consists the big right triangle PBC, and it also consists the right triangle PDC. And therefore, the area of trapezoid ABCD must be equal to the sum of the areas of the three components that it consists of. That is to say, the area of trapezoid ABCD must be equal to the area of the right small triangle ABP plus the area of the big right triangle PBC plus the area of the right triangle PDC. Okay, so what is the area of this small triangle ABP? The area of any triangle equals to the base of the triangle times the height over 2. The base is AB, that is A. The height is AP, that is A, divided by 2. So it is A times A over 2. That is to say, it is A squared over 2. The area of this right triangle APB, right small triangle APB equals to A squared over 2. Plus the area of the big triangle PQC. What is the area of the big triangle PQC? We choose the base, the area of the right triangle PBC. Again, it is the area of triangle PBC, the right triangle PBC. What is the area of the right triangle PBC? It is equal to the base, that is BC, times the height, that is QP over 2. The base BC is 4 plus 9, that is 13, times the height QP, that is 6 over 2. Again, the area of the big right triangle PBC equals to the base BC times the height PQ over 2. Plus the area of this triangle PDC. What is the area of triangle PDC? It is equal to the base DC times the height PD over 2. Again, it is the base DC times the height DP over 2. The base DC is B, the height DP is also B, divided by 2. So it is B times B over 2. That is to say, it is B squared over 2. The area of the right triangle PDC, in total it is B squared over 2. So, I shall find out that the area of trapezoid ABCD equals to, we have A squared over 2 plus B squared over 2. A squared over 2 plus B squared over 2 is A squared plus B squared over 2 plus the area of the big triangle, the big right triangle PBC. BC is 13, PQ is 6, divided by 2. So the area of the big right triangle PBC in total is equal to 13 times 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. So in total, the area of the big right triangle PBC is 39 square units. It's 39. So in total, the area of trapezoid ABCD equals to 169. Here we have A squared plus B squared. We already found out that A squared plus B squared equals to 169 over 2. So we substitute A squared plus B squared by 169 over 2. And finally found out that A squared plus B squared is 169 over 2 divided by 2. So it is 169 over 2 times 2 plus 39. 2 times 2 is 4, so in total, the area of trapezoid ABCD equals to 169 over 4 plus 39. Here, we multiplied 39 by 4 and then we divided by 4 in order to overcome factor with this number. And finally found out that 39 times 4 is 156. So in total, in the numerator, we have 169 plus 156 over 4. 169 plus 156 is 325 divided by 4. So the area of trapezoid ABCD equals to either 325 over 4 square units. In terms of numbers, the area of this trapezoid ABCD is equal to 81.25 square units. Okay, thank you very much.